the nice introduction. And first of all, I would like to say a few words of thanks to the organizer, because it's a great honor for me to present my work here at this very nice online conference. It's always very pleasant and to attend it, and I always learn a lot from it. So it's really nice that I could present my recent work here to you today. Also, for legal reasons, I need to mention that this work is funded by the Novo Nordisk Foundation and by a Marie Curie Fellowship. So with that being said, so what I will present to you today is some work I recently did with Prashant Singh, who is a postdoc in my research group, and it's about inferring entropy production for time-dependent systems. So let me start by saying a few words about inferring entropy production, because this is something that is kind of becoming a hot topic within the stochastic thermodynamics, and a lot of effort has been gone through it. Over the last couple of years. And essentially, the idea is that you observe some dynamical systems, like some molecular motors or something inside an environment, and you observe the dynamic quantities, but you do not directly observe how much entropy is being produced inside the system. And then the question is, to what extent can you infer from these dynamic quantities, from this information that you get, can you infer the amount of entropy that's being produced? So this can have many applications. For example, you might want to know how far from equilibrium your system is to see whether, for example, linear response theory holds. Or you might be interested in knowing how much energy is being consumed inside this part, for example, of a bigger system. Or you might wonder about the efficiency of a certain process. And so to do that, you need to infer the entropy production. So to do this, several methods have been developed. So I put some of the references here. There are really a lot of ideas on how to do this. For example, using these thermodynamic bounds, like this thing called the thermodynamic uncertainty relation. Or for example, you can look at waiting time distributions between subsequent events inside your system, or look at the asymmetry in trajectory. So how often is a trajectory seen versus the time inverted trajectory? That would also give you a measure of how much entropy is being produced. And there will be several other talks on this topic later on in this conference. But something that most of these papers focus on is on steady state systems. So systems where you have a constant gradient and then your system doesn't really change over time. It has a constant influx and outflux, and that's where the entropy production comes from. But there's also a broad class of systems where you actually have time-dependent driving. So from a theoretical point of view, you might, for example, think about Carnot cycle, but also in biological systems where you can, for example, see, like when you have some ATP-driven system, you might see some glycolytic oscillations, which effectively lead to time-dependent driving. So I would argue that it's also very important to look at this type of system when you think about the entropy production and you want to infer entropy production. So there are a few papers I could find that have talked about this. So, and essentially most of them focus on this thing called the thermodynamic uncertainty relation for time-dependent systems. And based on that, you can derive a number of methods to infer the entropy production. So something that, but a disadvantage of these methods, I would argue, is that you often need to measure quantities that might not be straightforward to measure. For example, you might need to measure a response function or some specific dynamic quantities, such as irreversible parts of fluxes, which might be challenging. And then an alternative to this is this machine learning-based method, where they essentially use machine learning and in combination with the thermodynamic uncertainty relation to infer the entropy production. But then you need quite a lot of trajectories, or something of the order of 10,000 trajectories. And so the question that we want to that we ask ourselves in this project is there a method to get a convenient method to measure entropy production of time-dependent systems with a limited number of trajectories, with dynamical quantities that are always easy to measure? For example, also if you cannot directly interact with the system. And in these cases, can you still infer entropy production from this? So that will be the main point that I want to discuss in this talk. And so to do this, I will focus on a broad class of systems, namely overdamped Fokker-Planck equation. So overdamped systems, overdamped continuous state systems. So the easiest way to think about this is, for example, a Brownian particle moving around in some environment, but you can also think of other types of systems like linear electronic networks, or for example, the magnetization of a spin. And so all of these equations satisfy this equation called Fokker-Planck equation, which is an evolution equation for the probability distribution of the system that you're looking at, where you have two terms essentially. So this first term is the force field, and second term is associated with diffusion. So this is an equation that you see a lot, where you can calculate the entropy production. So for this talk, I will focus on one-dimensional systems with constant diffusion coefficient, but I would like to mention at this point that you can also extend this to multidimensional systems or to systems with a spatially dependent diffusion coefficient, for example. I won't discuss about that here, but if you want to know more about this, you can always talk to me or send me a message or ask me after the talk. So anyway, for this type of systems, it's something that has been studied a few decades ago already, and it's kind of well established what the entropy production is. Because you can think about your standard thermodynamic course that the entropy production of this should be the system's entropy plus the amount of heat produced divided by the temperature. And so you can do some calculation, and then what you will find in the end is that the entropy production satisfies this equation here. Again, assuming a constant diffusion coefficient. But if you do this, and if you look at this formula, you can see that it satisfies all the basic quantities in the sense that this average entropy production is always positive. And if you go to an equilibrium state and you fill this in this velocity field, you can see that it goes to zero, and therefore the entropy production would go to zero. So it satisfies the basic ideas of an entropy production and can show that it generally works. So yeah, that's the kind of inputs that we take. And so what we now want to do is we want to, without like knowing all the, let's say you have some experimental setup where you don't know all the details of the system, like you don't, for example, know the force field and its time dependence, and you still want to get an idea of what the entropy production is for these reasons that I mentioned in the introduction. And as I already mentioned, we want to do this using quantities that are as simple as possible. And so in particular, the easiest thing that you could think of, you have this observable X, which is the observable that defines the system, like the position of the particle. So the easiest thing that we could think of was to just look at the first and the second moments. And then to observe lower bound, an estimate of the entropy production, what we would do, it's kind of a similar idea to what people do when they use, for example, the thermodynamic uncertainty relation. It's trying to find the tightest lower bound on the entropy production that you have that satisfies these equations for the first and second moment. So in other words, if you see the first moment change a lot throughout the protocol, you know that the entropy production will be higher than when it's constant in general. But the question is, can you quantify this? And the advantage of doing this is that because it's the tightest lower bound, it could still be a tight bound in general, because it is always achievable by some protocol. And on the other hand, it is always a lower bound, so you also know that it will always be higher, which is always some extra information, even if you don't know how tight the bound will be. Okay, so I won't go through the full derivation here, but just to give you a very basic idea, if you want to calculate the minimum amount of entropy production constrained on the first and second moment, what you will do, you might remember from your classes in calculus, that you use Lagrange multiplier. So we introduce this mu1 of t and this mu2 of t for these time-dependent moments, which you measure between time 0 and the final time tf, over which you want to calculate the total entropy production. Okay, and then you do some calculations. These calculations seem highly non-trivial at first glimpse, because you need to optimize this with respect to the time-dependent force field, because you want to calculate the force field that gives you the minimum amount of dissipation given this first and second moment over the entire duration of the protocol. And this seems quite non-trivial because you generally use because this depends non-locally in time on the force field, and so it's quite a difficult calculation, but there's a trick that's always also used, for example, when you think about the thermodynamic speed limit, which is changing to a coordinate system to co-moving coordinate, kind of like in fluid dynamics when you go from Eulerian to Lagrangian coordinates. And if you do this, the calculation becomes much simpler, and then you do some calculus, and what you will find in the end is that if you measure a first and a second moment, the total entropy production over the entire duration of the protocol will always be larger or equal than this integral here, which has two terms. So one term which only depends on the first moment, so the squared average rate at which your position changes. And then the other term only depends on the variance. So you have two separate non-negative contributions to the entropy production, where and the second term also depends on the variance squared. So in other words, the rate at which your variance changes and the rate at which your average changes determine the minimum amount of entropy production. And you can show that if you have full control over the force field, you can always saturate this equation. So yeah, this is kind of the first main result that I want to show you, because this is a very easy way to get a lower bound on the total entropy production of your system. And so a natural question to ask at this point is, can you extend this to higher moments? So in other words, instead of just measuring the first and the second moment of the observable that you're looking at, can you also look at the first 3 or 4 moments and get a similar bound? And the answer to that is a bit yes and no, because you cannot, as far as we could solve it, we could not reduce it to simple, elegant, easy equation like we did before. But you can reduce it to a set of equations that look quite horrible if you look at it, but they are quite easy to integrate numerically. So what you would do is you would give your time-dependent moments that you measure, you put them into this into this set of equations, and then what rolls out is a numerical lower bound for the entropy production. So this would be a tighter bound because it's more constrained on more moments, but the algorithm is a bit less stable. So one generally sees that it has less that you need more data to apply it, but I will talk a little bit more about that later on in my talk. So anyway, this was from a theoretical point of view what I want to tell you. So the question obviously is how well does this work? In other words, can you get a good estimate of end-to-end reproduction with this? And so to do this, we first thought we tested it on a few very simple theoretical toy models. So the simplest thing you can think about, in my opinion, would be a moving parabola, but you can already show that for this for that equation, this lower bound becomes exact, so that would be an optimal protocol. And so you can show that lower bound is exact, and it's not very interesting, or in a way it is interesting, but there's not that much to say about it, and this has been established already a long time ago. So we thought about looking at slightly more complicated system, namely that of free diffusion, where you have some particle doing Brownian motion around, first in some confined potential, and then at time zero, you remove the potential and you just let the particle run around and spread over space. So there won't be any heat production because potential is just flat at all times. But on the other hand, you will lose information, so there will be, because the particles spread out, so there will be Shannon entropy produced, so the system's entropy will change. And you can solve this exactly, and you can calculate the change in entropy. And so change in entropy is the change in Shannon entropy between time zero and time tf. And so if you would just start with a delta peak, again, this would become, or with a Gaussian potential, this would again become exact. So we looked at something slightly different, namely a quartic probability distribution. And for this quartic probability distribution, you can calculate both the exact entropy production and the first and second moment, which you then can put into your lower bound to measure the real entropy production, to get the lower bound of entropy production, And then you can compare the two, and this is what we get. So the red curve here is the exact entropy production, and the green dots are the lower bound based on just measuring the first two moments. And so as you can see, already they are in very good agreement. You can clearly see that they follow the same trend and they get similar results. But the question then is, can you do even better if you add more moments? And the answer turns out to be yes. So for example, if you look at the first 4 moments, you can see that they're essentially the same as the real entropy production inside the system. Okay, so before coming to a more complicated example, just another way of looking at this would be the error of the estimate. So essentially how far you are off from the real entropy production divided by the real entropy production. So for very small dissipation, turns out that this is a bit higher because the real entropy production is quite low, and so even a small difference would already be a high relative error. But you can see in general that even with just using the first 2 moments, you already get an error of only 5% of the real entropy production. And then if you add 4 moments, you go easily below 1% difference from the real entropy production in this simple system. So it turns out it works quite well. Okay, so there is another point. I don't think I have time to go through it here. It's about like a different method to infer the entropy production. If anyone is interested, in talk about it a bit more. But instead I will talk about in my opinion much more interesting example, which is that of bit erasure. Because at this point, this was all theoretical simple toy models, and it's maybe not that surprising that it works very well for these very simple toy models. But so what we wanted to do was to actually apply this method to experimental data. Now, luckily, I used to be a postdoc in an experimental group in Vancouver, in the group of Sean Beckhofer, and he's a real expert on this bit erasure. And so I asked him for some data of process doing bit erasure to essentially measure the entropy production. So essentially, the idea here is that you have a bit which is initially in equilibrium. So the bit is essentially, can be either in state 0 or 1. It's a double well potential. If you're in left hand well, you're in state 0. If you're in right hand well, you're in state 1. Then you can show that if you start from an equilibrium state with equal probabilities and you want to push all the probability to one state, you can show that the amount of work that you need to do or the amount of heat that you produce will always be at least kBT log 2. This is the Landover limit. There has been a lot of interesting experimental work that has been done on this over the last decade or so. And so we wanted to use some of that experimental data to actually test our bound. And so the nice thing about this is that on one hand, it's simple enough to really estimate how well the method works, because you can, in simulations, calculate the real entropy production. And on the other hand, you can measure the first and second moment, so you can easily compare them with each other to get a hang of how well this works in real experimental systems. So I should mention for completeness that the data that we got was something from an asymmetric bit erasure experiment, or one well is a bit bigger than the other. But anyway, so this is the protocol that you follow. I'm not going to go through the details here for time constraints. But instead, I want to talk a bit about the experimental data, because when we got the data, we were a bit scared in the beginning, because as you can see, they do the bit erasure at different speeds, and for each speed they had a number of trajectories, and this number of trajectories was quite limited. So it's of the order of 10, 20, 30 trajectories for each duration. And so this is much less than people typically use in inferring entropy reproduction. In general, one talks about the order of 1,000 or even 10,000 of trajectories. So at this point, I didn't really believe that it would work, but I asked my postdoc Prashant to have a look at it anyway. And so what he did was actually to just plot the data, the first and second moment, and then just as you can see, the data is somewhat noisy. You cannot directly calculate the first and second derivative, which you need, or at least first derivative, which you need to calculate the entropy product, the lower bound on the entropy production. So instead, we fitted it to a high number of Chebyshev polynomials, and just so that we can smooth it, and so that we can essentially estimate the first and second derivative, the first derivative of both first and second moment. So here you see one of the examples for durations of, I believe, 10 units of time. So, but I think it's about half a second. And so anyway, this gets us a good estimate for the first and second moment of the data. And so at that point, we can compare it with simulations, with simulations, which essentially should be able to give us the real entropy production, because there's a rather good mapping between experiment and simulations, I would say. So you can run the simulation and get the exact entropy production to see how well the method works. So this is theory, and then we applied the data to it. And as you can see, even though we only have like a few dozens of trajectories, we still get a very good agreement between the simulation and the experimental data. So it turns out that this method seems to work, at least for this type of experiment, seems to work very well in estimating the real entropy production of the system. And so this is what I want to talk to you about today, and I see I'm just in time. So essentially what we have derived is a method to infer entropy production for time-dependent systems based on simple quantities that can be measured experimentally and that don't need a lot of data. And it turns out that it's in very good agreement with the experimental data. And if you want to know more about it, the paper is currently on arXiv. So thanks for giving me the opportunity to talk, and I welcome any questions.